All right, in this video, we're going to ask ourselves what the central bet is that cells make so they have directionality rather than just sort of sitting there and flopping around. So let's get into that. All right, so in the last video, we talked about how cells have this problem. And that problem is that their parts are all small and are thus being buffeted by water. And the mental picture that we can have is imagine yourself surrounded by softballs, dropped into a martini mixer and shaken vigorously. That's the experience of proteins. Yet somehow cells achieve this beautiful ordered outcome, this ordered behavior, even though their parts are all being shaken around. And we talked about how cells do this by playing the long game. That is, all the molecular motions are happening on a fast time scale, but cellular behavior is happening on a slow time scale. And that's analogous to buying stocks early and holding on to them for a long time, so that the overall trend of getting money in the market is overcomes all the random fluctuations, right? The random day-to-day fluctuations. Cool. We describe this in cells as a separation of time scales. So things like metabolic pathways in cell biology run thousands to millions of times slower than molecular motions. So we can average out this randomness by waiting a long time. But we have a problem, and maybe you've seen it already. And that problem is that what are we betting on, right? So in a stock market situation, when we're betting that the market will go up. The investors are saying, for whatever reason, we think that the stocks are going to continue to have increasing value. But imagine a different sort of thing we're betting on that just randomly fluctuates around and doesn't have a trend to it. So this is random fluctuations. If I bought here and I sold here, I would have made $0, right? Waiting a long time in a system just that's randomly fluctuating doesn't help you. You need a system where there's a directionality to it, where it's going somewhere. And so the question we're going to be thinking about here is, what is the central bet that's made by cells? What is the equivalent to betting the stock market will go up for a cell? So it turns out they all make similar bets, and here are the core bets that are made by 5 different organisms. So this is a good point to pause. So pause and think about for a second, what unifies all 5 of these reactions? So pause, unpause. All right, you unpause. I am going to say that all of these reactions are redox reactions. Super exciting. Now, if you're like a lot of students in the classes I teach, your face has just fallen because you're like, oh no, redox is so complicated. Cells love redox. So we're going to be doing a lot of redox chemistry in this class. But don't worry, we're not going to deal with it right now. For the moment, we're just going to say that redox, these are all spontaneous redox reactions. So these are reactions that are going to happen, right? If I put a lot of hydrogen gas around with carbon dioxide and wait long enough, eventually we're going to end up here. We're going to end up with methane and water. Here's another example down here at the bottom. This is glucose interacting with oxygen. This is the one that we run. This reaction is exactly the same reaction as a campfire, right? We're basically burning sugars with oxygen. So oxygen's coming in here. It's getting turned into carbon dioxide and water, consuming glucose along the way. Okay, so what we're seeing is that cells at the center core of their metabolisms are betting on some kind of spontaneous redox reaction. Why is that a good place to bet? To look at this, let's actually look at this top reaction here. This is something that's done by a class of organisms called methanogens. And it turns out physical processes actually generate redox reactants. So a bunch of geophysical processes will spit out something like a hot spring, things like hydrogen gas, carbon dioxide. That's all happening sort of in this environment here of a thermal vent, a hot spring. There's the word I'm looking for, this hot spring. So it turns out an organism just has a ready supply of hydrogen gas and carbon dioxide, so it can go on and do this reaction. So basically, there's always a directionality, right? We're always flowing. We're making hydrogen. We're making carbon dioxide. Let's make methane and water. And so what cells are doing is they're betting on environmental redox chemistry. One way to think about this is there's the environment is already producing these molecules. Those molecules are eventually going to react with each other anyway. So all that life is doing is just hooking into that along the way. And so I like this picture of the little piggy with its pinwheels. The car is moving along. It's making wind, and just stick out the pinwheels and they're going to spin like crazy. That's one way to think about what organisms are doing. But actually, we can be a little bit more precise than that without getting too complicated. Metabolism obviously becomes a very complicated beast, but let's just look at this practically. What does it mean when we say that a cell is betting on a favorable redox reaction? And to illustrate this, I'm actually going to switch away from methanogens and talk about us. So what we're doing is our cells are taking in glucose and they're taking in oxygen, and they are oxidizing the glucose into carbon dioxide, reducing the oxygen into water. And through this cycle, this is a very favorable reaction. So practically what they've done is they find or use a favorable redox reaction. So that's step one. Basically, every living organism has some central favorable redox reaction at the center of it. Second step is to break reaction into steps. So in this case, what I'm doing is this is actually simplified relative to how it really works in cells, of course. But basically what we're seeing is there's this cycling between NAD+, which we will talk about in detail later, and NADH that basically acts as the mediation, the bridge between glucose and oxygen. So this whole process is still super favorable, but now instead of doing it in one whack, one go, where we say light the cell on fire, we've actually broken it into a bunch of intermediate steps where we're generating things like NADH. That leads to step 3, which I'm going to make myself go away here. Step 3 is we then couple intermediates to other pathways. And so what we're seeing here is NADH can cycle back to NAD+. Turns out that can be used to turn acetate into fat, right? So we can build molecules like fat by coupling into this existing flow, right? So this is a super favorable thing that's happening, that's just always happening. Cells are taking in glucose, they're burning it, they're making carbon dioxide. That favorable process can be used along the way to spin out and make new interesting molecules like fats. And this sounds complicated and sort of Byzantine, and like, how could this actually work? But it turns out it's actually favorable to make ordered systems if they increase the rate of a reaction. And so this is a very physical example of this. I don't know if you've ever done this, where you've filled a water bottle with water and then you dump it out. And if it has a narrow enough neck, the water sort of glugs out slowly, right? But if you take that same water bottle and you spin it while it's going down to make a whirlpool, it'll rapidly drain all of the water out. In that rapidly spinning vortex, you're creating order, right? This vortex has all this interesting dynamic order and these like ridges that are forming, right? It's this beautiful ordered thing, but it's favorable because it's actually speeding up the rate the water goes out of the water bottle. It's the same thing here, that life is speeding up the rate that we break down molecules, and that turns out it's favorable to like build a complicated ordered thing. So let's actually show this with sort of a thought experiment. So life increases the rate of equilibration of a reaction, right? So this reaction, it is extraordinarily favorable for glucose to interact with oxygen to form carbon dioxide and water. But you have glucose in your kitchen, or at least something like glucose. And so imagine you throw that glucose into maybe a cup of water, and you sit there and watch it and ask yourself, what is the concentration of glucose as a function of time? The answer is going to be something like this, right? Even though it's favorable to break down glucose, it just sits there, right? There's nothing overcoming the activation barrier to actually do the reaction. Even though it's favorable, it's very, very slow. Now imagine that you add a bacterium that eats glucose into that system. What's going to happen? So that's actually a good point. Pause and think about it for a second. What kind of curve should I draw here when I add a bacterium that eats glucose? Okay, I'm assuming you pause. We come back from the pause, and what we see is the glucose concentration rapidly goes away. We rapidly turn that glucose into carbon dioxide because the bacteria are sitting there and they're eating it. They're speeding up that reaction. And so what that means is that cells are fundamentally making a bet on environmental redox chemistry, that there's going to exist a set of reactants where it's favorable to do redox chemistry, and those reactants are generated by physical processes, geochemical processes. Turns out that photosynthesis is basically this too, so photons are coming in. They get this central redox chemistry bet. They're going to couple that central favorable redox reaction to other reactions, creating some complicated network of reactions. That complicated network of reactions is favorable because it lets the cell do that central reaction faster. Basically, it can rapidly consume that fuel, and that higher speed of consumption means that the cell has energy available to build extra order. Okay, so that was maybe a little bit wild and complicated and abstract, but hopefully it gives some notion for what cells are doing. When we say that, oh, cells are consuming energy, they're following some energy gradient, that's what they're doing. They're grabbing onto some existing reactants, turning them into products rapidly, and sort of making order along the way. Okay, so thanks for watching this video. Look forward to seeing you next time.